Carbon Capture, Utilization and Storage or CCUS, Comprehensive Overview. Techniques to reduce emissions and combat climate change. Introduction to CCUS, why CCUS matters, what is CCUS? Carbon capture, utilization, and storage or CCUS is a critical technology for achieving global climate targets and mitigating greenhouse gas emissions. It addresses hard-to-abate sectors such as oil and gas, power generation, and heavy industry, where direct electrification or renewable substitution is not yet feasible. CCUS complements renewable energy and energy efficiency measures by capturing CO2 emissions from point sources or directly from the atmosphere, preventing their release into the environment. This technology is essential for countries and companies striving to meet net zero commitments, as it enables continued industrial activity while reducing carbon intensity. CCUS also plays a role in negative emission strategies when combined with bioenergy or direct air capture, making it indispensable for long-term climate stabilization. CCUS encompasses a full value chain, capturing CO2 from industrial processes or power generation, conditioning and compressing it for transport, and either utilizing it in industrial applications or storing it permanently in geological formations. Capture technologies include post-combustion systems using chemical solvents, pre-combustion methods integrated into gasification processes, and direct air capture for atmospheric CO2 removal. Transport typically involves pipelines or shipping for offshore storage. Utilization pathways include enhanced oil recovery, chemical synthesis, and mineralization in construction materials. Geological storage occurs in deep saline aquifers or depleted oil and gas reservoirs, secured by impermeable caprock layers. Monitoring and verification ensure containment integrity and regulatory compliance throughout the life cycle. Objectives and scope of carbon capture, utilization and storage or CCUS. The primary objectives of CCUS are to reduce greenhouse gas emissions, enable low-carbon industrial operations, and support compliance with climate regulations and ESG commitments. CCUS helps companies avoid carbon taxes and meet emissions trading obligations, while preserving the economic viability of critical assets. It also creates opportunities for monetizing captured CO2 through utilization in chemicals, fuels, and construction materials. By integrating CCUS into industrial processes, organizations can maintain operational continuity during the energy transition and contribute to global decarbonization goals. The scope of CCUS projects typically include CO2 capture from point sources such as power plants, refineries, and cement kilns, compression and dehydration for transport, pipeline or shipping logistics, utilization in industrial processes, and permanent geological storage. It also encompasses monitoring, measurement, and verification, MMV, systems to ensure containment and environmental safety. Project boundaries may extend to shared infrastructure models, known as CCUS hubs, which aggregate CO2 from multiple emitters to reduce costs and accelerate deployment. Capture technologies, transport and storage. CO2 capture methods include post-combustion systems that remove CO2 from flue gas using chemical solvents such as amines, pre-combustion capture integrated into gasification processes, and oxy-fuel combustion that produces a concentrated CO2 stream. Direct air capture, DAC, is an emerging technology that extracts CO2 directly from ambient air using sorbents or solvents. Each method has distinct technical and economic characteristics, with post-combustion being most common for retrofits and DAC offering potential for negative emissions. After capture, CO2 is conditioned through dehydration and compression to meet transport specifications. Pipelines are the most cost-effective option for large volumes, while shipping is suitable for offshore storage. Geological storage involves injecting CO2 into deep saline aquifers or depleted oil and gas reservoirs, where it is trapped by impermeable caprock layers. Long-term containment is ensured through structural, residual, solubility, and mineral trapping mechanisms. Monitoring technologies such as 4D seismic surveys and pressure sensors verify storage integrity over decades. Cost structure and financial drivers. CCUS economics are dominated by high upfront capital expenditure, CAPEX, for capture units, compression systems, pipelines, and storage facilities. Operating costs, OPEX, include energy penalties for solvent regeneration and compression, solvent replacement, and monitoring expenses. Cost per ton of CO2 captured varies by sector, $20-40 for natural gas processing, $60 to $120 for power generation, and $70 to $150 for cement and steel. Revenue streams include carbon tax avoidance, emissions trading credits, and CO2 utilization. Government incentives such as tax credits and grants are critical for project viability. Shared infrastructure models, known as CCUS hubs, improve economics by distributing costs among multiple emitters. Oil and gas, power generation, cement and industrial. In oil and gas, CCUS is applied to gas processing, LNG facilities, and hydrogen production units where CO2 streams are relatively pure, reducing capture costs. Offshore storage in depleted reservoirs leverages existing subsurface expertise and infrastructure. Integration with blue hydrogen projects enhances the sector's decarbonization strategy. Inspection and integrity management are critical for CO2 pipelines and injection wells, requiring specialized materials and monitoring protocols. CCUS enables coal and gas-fired power plants to reduce emissions while maintaining grid stability. Post-combustion capture retrofits are common, though they impose an energy penalty of 15 to 30% on plant output. Economics depend on carbon pricing and policy support. CCUS in power generation provides dispatchable low-carbon electricity, complementing intermittent renewables and supporting system adequacy. CCUS is essential for cement and steel industries because their process emissions cannot be eliminated through electrification alone. Capture technologies such as calcium looping and amine systems are integrated into kiln and furnace operations. Utilization pathways include mineralization in concrete curing, but geological storage remains necessary for large-scale impact. CCUS ensures compliance with tightening emissions regulations and supports sustainable construction practices. Key risks and challenges, future trends and innovations. CCUS projects face risks including high capital costs, energy penalties, policy uncertainty, and public acceptance challenges. Technical risks involve solvent degradation, pipeline corrosion, and subsurface injectivity variability. Mitigation strategies include robust design, redundancy, stakeholder engagement, and regulatory compliance frameworks. Emerging trends in CCUS include the development of shared infrastructure hubs, integration with hydrogen production, and deployment of negative emissions technologies such as BCCS and DAC. Advances in materials, solvents, and digital monitoring systems are reducing costs and improving reliability. Artificial intelligence and digital twins are being applied to optimize operations and predict subsurface behavior, enhancing safety and efficiency. Conclusions and recommendations. CCUS is a proven technology that plays a vital role in achieving net zero emissions. While economic and policy challenges remain, its technical feasibility has been demonstrated across multiple sectors and geographies. CCUS complements renewable energy and electrification strategies, providing a pathway for decarbonizing hard-to-abate industries. Organizations should prioritize CCUS deployment in high-purity CO2 streams to minimize costs, leverage shared infrastructure hubs to improve economics, and secure policy support through engagement with regulators and industry alliances. Early adoption of advanced monitoring technologies and integration with hydrogen and negative emission strategies will position companies for long-term success in a low-carbon economy.